Welcome students to our another class of electricity and magnetism. This is the third class of electricity and magnetism, and we have studied about alternating current, direct current, its applications, the current time graph. We also studied about the magnetic effect due to current in different kinds of wires like straight, circular and solenoid. We even visualized all these using some of these using the experiment as well. So today we will be studying about magnetic flux. What is magnetic flux and why is it important for our upcoming topic, electromagnetic induction, and how we can use Fleming's right hand rule in this case, and also about the Faraday's law of electromagnetic induction and bicycle dynamo, which is also the application of electromagnetic induction. So today our major topic is electromagnetic induction, but before diving into the main topic, we have to know some basics about the term magnetic flux. So we know about magnet, we know about magnetic field, we know about magnetic field lines, we know some basic characteristics of magnetic field lines as well. Magnetic field lines, they do not overlap on each other, they have their separate path. And another one was, yes, magnetic field lines, they always go from the north pole to the south pole. Okay, so now what is this term magnetic flux? Let me tell you, it's a simple definition. It is simply the measure of magnetic field lines which enter the area of a certain object which is kept right in the magnetic field. Let me show you in this way. Let's say this is a magnet. This is a magnet. Let's not just say it is a bar magnet, and this bar magnet has magnetic field lines around it. We know that, right? So now when this magnetic field lines, okay, let me place one small piece of paper here, or let's say some conductor. Okay, so we know the magnetic field lines are entering the surface area of this object. Okay, so the measure of magnetic field lines which enter on the surface area when placed in a magnetic field of particular magnet is known as magnetic flux. So how does it vary? Let's say we know the magnetic field lines are quite stronger near the poles, right? So whenever there is magnetic field line, whenever the magnetic field lines are stronger, we always show it by many arrows. If there are many arrows, it means the magnetic field is very strong, the magnetic field strength is quite high. But if the lines are few, it means the magnetic field strength is also less. Okay, so let me show you. This is a sample of one simple object which we have placed in this magnetic field. You can see only two magnetic field lines have entered this object. So that is the measure of magnetic flux. Let's say same object is being placed at another path. See, here the magnetic field is quite strong. How do you know that? You can see the magnetic field lines are many in number comparatively to this part. So here you can see the magnetic flux is also quite high because the number of magnetic field lines which have entered this area is more. Similarly, let me show you one last one. It has been placed, this same object, if it is been placed a bit further than the other magnetic field lines, you can see only one magnetic field line have entered the surface area. So in this way, where you place the object varies the measure of magnetic flux as well, because it varies the number of magnetic field lines which enter the surface area. So basically magnetic flux is a measure of the total magnetic field passing through a given area, and it also quantifies on how much magnetic field is flowing through a surface. So it is denoted by the symbol phi, as you can see on the screen, and we measure it in Weber. It is name of a scientist, and we use it as the SI unit of magnetic flux. We measure it in Weber, which is also written as WB as on there. Okay, so now let's see, as we already know about the difference or change in magnetic flux where the objects have been placed, right? So now let's see on what characteristics, or let's say on what conditions does this magnetic flux depend. Firstly, flux is proportional to magnetic field strength. As I already told you, the magnetic field lines are quite higher near it, right? Means if you place an object very close to it, of course the magnetic field lines which enter this object is also greater. So, which means the magnetic flux is very much greater in case of this magnetic field strength. If you place it further, the magnetic field is also quite low, which makes the magnetic flux also very low. This means that magnetic flux is directly proportional to magnetic field strength. Okay, another one is it varies on how the surface of conductor faces the direction of magnetic field. So this is a magnet again, and if I place this conductor in this angle, you can visualize the number of magnetic field lines that enter this has been minimized. But what if I place this in this way? Meaning the number of magnetic field lines which enter this conductor has also increased. So that is another parameter on which magnetic flux depends. Third one is it also is directly proportional to the area of the conductor. Let me show you this using a very small piece of paper. Here you can see papers of two different sizes. One is of this size, and comparatively you can see this is smaller than this. So if I place this, let us say this is a conductor. If I place this conductor in the magnetic field of this magnet, let's say it's here, okay, and if the magnetic field lines go around this area of the conductor, means all the magnetic field lines are not able to enter this conductor. Why? Because of its less area. But what if I use another conductor of this size? This means many more magnetic field lines will enter in this conductor in comparison to the smaller one, right? Okay, so I hope you have understood about the very basic concepts of magnetic flux. So why are we studying about magnetic flux? You will understand it now. Okay, now our next topic, subtopic is electromagnetic induction. And if you look at this image, I think you can recall this image from our previous class, right? Can you remember it? Yes, this was the image that we used when we were learning about the magnetic effect due to current in a straight wire. Okay, why am I reminding you this? Okay, we know that when in a conductor, if current is being flowed, if current is being sent, what happens? Magnetic field is being generated. Okay, so now let us imagine a scenario where you have given no source of current or voltage, but still your conductor can gain voltage. Can you imagine that situation? Or have you already studied about it somewhere else? Okay, if not, don't worry. We know how magnetic flux varies, right? I will show you it in a small video right now, but before that, let me again recall you. Now you know that magnetic flux, if you place near the magnetic flux is high. If you place it further, the magnetic flux is low. What if you keep on moving the conductor or the magnet or both of it? What happens? Exactly. Magnetic flux also varies if you change or move magnet or the conductor like this. We know that, right? When we move any conductor or magnet, the magnetic flux starts to vary. Now what happens when when magnetic flux varies in case of conductor? EMF is induced, or let's say electric current starts to flow in that conductor. This is the concept of electromagnetic induction. How did they do this experiment? We can imagine a galvanometer being connected. Let me show you this video. You can see this is a galvanometer. So galvanometer is a device which can even detect very small amount of current as well. Okay, so even the smallest current can be detected by this galvanometer. If current flows, you can see it will show deflection. Now let me show you this whole system. Here you can see a solenoid, right? You know, you are able to recognize solenoid now, right? So one end of the solenoid is being connected to the positive terminal, another one is being connected to the negative terminal, and in between you can see there is a bulb. So now here you can see the magnet is being moved inside this solenoid. So when this magnetic flux varies, by moving this magnet, we can see that there is the flow of current, there is some current being induced, which is helping this bulb to light on. Okay, so in times you can see that this bulb is not like, it's not always switch on. Here you cannot see the light, right? Why? Because in that particular case the magnetic flux is not changing. So the basic concept of electromagnetic induction is that the process of inducing EMF, that is voltage in a conductor, when there is a change in magnetic flux linked with that conductor. Here the terms that you might be confused might be EMF, right? It is electromotive force, although you have already studied it in grade 9. So what exactly is electromotive force? Electromotive force is the force which pushes the electrons throughout the conductor, causing to generate the current. Okay, so means when there is the change in magnetic flux beside the conductor, what happens? The conductor starts to gain EMF. Such EMF is known as induced EMF, because it has been induced by the change of the magnetic flux. And this concept was discovered by Michael Faraday, and it is very widely used in power generation, transformers and other electrical devices, which you will learn more about in transformer and power generations. Okay, now we know that not only that current has its effect, or let's say not only the current can give magnetic field strength, but even some magnetic flux, change in magnetic flux can give us current. Let us recall, when there was magnetic field being generated, we had to know the direction of the magnetic field. Okay, because we already knew about the direction of the current, we knew about everything else, we didn't know about the direction of the magnetic field generated. Now what is being generated? Earlier it was magnetic field. Right now what has been generated? Yes, right now current is being generated, right? Electromotive force is generating current, is helping to induce current. Now we have to know the direction of the current. Now how can we know the direction of the current? Earlier we had right hand thumb rule, right hand grip rule, right? I hope you remember that pretty well. Now we need something called Fleming's right hand rule. It's again the right hand rule, but it is Fleming's right hand rule. Now to understand this Fleming's right hand rule, let's say you need a right hand. You need these 3 fingers. Earlier in case of, let me recall you what you did in case of thumb and grip. The process was same. You grabbed a pen, you did your thumb in this way. In case of right hand thumb rule, the thumb denotes what again? Yes, the thumb denotes the direction of current. In case of grip rule, when you did this way, the grip denotes what again? Yes, the grip also denotes the direction of the current. Whatever rule it is, it denoted the direction of the current. So now it is a bit different than what we studied in our earlier class. Here it is Fleming's right hand rule. Here you can see a U-shaped magnet. Right, we will be using this magnet because we need north and south pole facing towards each other. Now from this what information do you have so far? Nothing, right? You just have a magnet, it is U-shaped. Let's say a conductor is being passed. Okay, this represents the conductor. Okay, now we have 2 information. First, we have a U-shaped magnet and we have a conductor being passed from this magnet in between. And from this scenario, you must be able to say one more thing. Can you guess what it is? From this, you should know that the magnetic field lines, what we studied earlier, we revised it as well. The magnetic field lines always go from the north to the south pole. Okay, so now what do we have again? The magnetic field, we have the direction of the magnetic field lines. We have a conductor which is passing from this magnet in between. Okay, now what we will do, we will suppose that this conductor is being moved in upward direction. What happens if we change the, or let's say if we bring motion to a magnet or a conductor, if they are in a magnetic field? Exactly. EMF will be induced, or let's say this conductor will gain current. The current will start to flow from this conductor. Okay, so now let's say this conductor is being moved in upward direction. Okay, now you have two things, two important things. You know the direction of the motion, it is upward because we will be moving this upward, and you know the direction of the magnetic field lines, this, it is going from north pole to south pole. Okay, two important details. Again, let me remind. Magnetic field lines, we have the direction of the magnetic field lines, we have a conductor which has been passed through it, and now we also have the motion which is upward direction. Okay, now the only thing we need to know is the direction of the current. So now this is where we use Fleming's right hand rule. To use this rule, you have to use your thumb, your forefinger, your middle finger. Okay, first place these three fingers perpendicular to each other. See, this is perpendicular to this is perpendicular to this. Okay, once you do this, you can see in the diagram as well, I have mentioned that the thumb gives the direction of the motion. Okay, now look at the image. The motion is upward direction, right? Now, if thumb is the upward direction, which is shown in this way, and the magnetic field, just follow my finger instead of the diagram. Okay, right now, see, the magnetic field is in this direction, right? See, from north to south, you can compare it in the diagram as well. So we have the direction of this, we have the direction of the motion, which is denoted by thumb. We have the direction of the magnetic field. See, it resembles the image as well. Now we have this middle finger remaining. What does this middle finger show us? It shows the direction of the current. So if you follow Fleming's right hand rule right this way, showing as in the image, you will see that the current is going inwardly in this direction, right? So what happened, what did we study right now? We are going to place a U-shaped magnet where the magnetic field lines are going from north to south pole. We placed a conductor. We did not know where the direction of the current was earlier, right? So we placed a conductor passing through it, and we moved this conductor in upward direction. Why is the EMF being induced? Because when this conductor is being moved in upward direction, magnetic flux is being changed. So to know the direction of the current induced, what did we do? We used this Fleming's right hand rule, where the thumb showed the direction of the motion and these three were placed perpendicularly. And if you follow this Fleming's right hand rule, and if you compare it with the given image, you will be able to know that the direction of the current was towards inward direction. Okay, from this you should know that Fleming's right hand rule is used to determine the direction of induced current in a conductor moving in a magnetic field. It is already based on the concept of electromagnetic induction. Another one, how did we do this? We stretched our right hand with the thumb, index and middle finger perpendicular to each other. I mentioned that, right? And these are the points that you should remember. Thumb, direction of motion, and index finger is the direction of magnetic field, and middle finger shows the direction of induced current. Okay, so the direction of the current is also dependent on the direction of motion. Okay, right now we did one simple example. On our upcoming classes we will show that in much more detail. Okay, so again recall this: thumb, index finger and middle finger. Thumb showing the direction of the motion, index finger showing the direction of the magnetic field lines, and middle finger showing the direction of the current. We will follow this rule for our upcoming classes as well, so please study it carefully. So now, based on this principle, Faraday generated some laws and called it Faraday's law of electromagnetic induction, which are also known as principle of generators. Now, firstly, he said that whenever the magnetic flux linked with a circuit changes, an electromotive force is induced in the circuit. We already studied about this concept, right? And we can again visualize it in this video as well. You can see when the magnetic flux is being changed by the motion of the magnet, the EMF is being induced in that shown solenoid right here. And the second one is the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux. Let me show you again. If this is a magnet, and again we are placing this in a magnetic field. Okay, let's say we are placing this in a magnetic field. What happens if I keep on moving this? The magnetic flux is changed. What if I increase the rate of motion? If I increase the rate of motion, the rate of magnetic flux change will also increase, which will again, what happens, the magnitude of the induced EMF will also increase, meaning that such induced EMF is directly proportional to the rate of change of magnetic flux. Okay, so now we have some basic things to again recall about. Or in our earlier class, we were studying about the magnetic effect due to flow of current in a conductor, right? In our today's class, what did we focus mainly? We focused about the effect of magnet. Let's say we can say effect of magnet in producing EMF, or let's say in producing the current in a conductor. Okay, so for this, what did we do? We used a U-shaped magnet, and we used Fleming's and we used Fleming's right hand rule to know the direction of the current which was being generated. For that, what did we do again? Yes, we placed our three fingers perpendicular to each other, and the thumb was the direction of the motion of the conductor, which in our case was upwards. This finger showed the index finger showed the direction of the magnetic field lines, whereas the middle finger showed the direction of the induced current. Right. So, what is induced EMF? I think now you can answer that, right? What exactly is induced EMF? The EMF which is being induced by this process, okay, is known as induced EMF, and EMF is simply the electromotive force. Electromotive force, what is it? It is the force which pushes the electrons throughout the conductor. Okay, now with this basic concept of our today's class, we will now proceed to our another subtopic, which is known as dynamo. I think you have heard about dynamo. How many of you know about dynamo? Okay, so I think many of you have heard about it. And what exactly is it in terms of science? It is a device that converts mechanical energy into electrical energy. You have the basic concept about mechanical energy as well, such as kinetic and potential energy. They are the type of mechanical energy. So dynamo basically converts this energy into electrical energy. So it also works on the Faraday's law of electromagnetic induction, means it is the application of that particular principle. And it states that an electric current is induced in a conductor when it moves through a magnetic field. We already studied about it. So the term dynamo, I think you might have heard it with some other word. And it might be bicycle, because in bicycle, dynamo is used to power its light. Okay, so now you know in cycle, if they have to power their lights, they use dynamo. Now what exactly is the working structure of dynamo? Let me show you this in your next slide. Okay, again, do not panic when you see these diagrams. I'm going to explain it to you one by one. First, let's not look at the other image. Let's just look at this part. Here you can see at the head, this is the head part of this dynamo, and this dynamo is connected by an arm which is also known as spindle. This spindle is connected to a permanent magnet. We have to use a magnet where you can keep the north pole and south pole facing towards each other. Okay, let me again tell you this. This is the head part, this is the spindle part, which is also known as armature or axle, and this is connected to a permanent magnet, and around this is a coil of wire. From this coil, one end is also brought outside and another end is also brought outside. You can see this, right? And this is being connected to the lamp. Now let's see what happens here. This dynamo is placed near this tire, and we know when tire moves, obviously the head part is going to move. Now I think you are going to again reconnect it with whatever you studied today. Let's see. This head part, when connected to the tire as shown in this diagram, what happens? Once the person starts to ride this cycle, this tire starts to move. When this tire starts to move, this head starts to move. And you can see the head is connected with the spindle, so spindle also starts to rotate. When the spindle starts to rotate, you can see these permanent magnets are also starting to rotate. Now, what is the concept behind this? We know when magnet or conductor comes into motion in a magnetic field, what happens? Magnetic flux changes. So when these magnets start to rotate around, what happens is magnetic flux starts changing, and the conductor around this coil starts to gain EMF. Here we can see the EMF has been induced, and when these wires are being connected to the lamp, you can see it gives power to this lamp which is held in front of the bicycle. Okay, so again it is the concept of electromagnetic induction. What is happening here? Let's see, dynamo is being attached to attached to its tire, the tire of the cycle. When you start to ride this cycle, obviously the tire starts to rotate. When the tire starts to rotate, since it is being connected, or let's say it is being in touch with the head of the dynamo, the head of the dynamo also starts to rotate. When head of the dynamo starts to rotate, the spindle starts to rotate. And since the spindle is connected to the magnets, the permanent magnets, these magnets also start to rotate. When the magnet starts rotating, what happens is magnetic flux changes around this area. And due to the change in magnetic flux, these coils start to gain EMF, or let's say EMF is being induced in this coil. Since the coils are being again connected to the lamp which is in front of the bicycle, after the change of the magnetic flux, this induced EMF gives current, and then this lamp gains power. This is how a dynamo works. So talking about the working of dynamo, you can say when the wheel of the bicycle rotates, it causes the head of the dynamo to spin, which in turn rotates the permanent magnet. Thus, the magnetic flux passing through the coil changes and an EMF is induced in it. It induces direct current in the circuit. So now if you are using a cycle and if you have to ride it in night time and all, you can use a simple dynamo, where this dynamo is going to convert the mechanical energy into electrical energy, and it will help you in your daily life as well. So which mechanical energy are we talking about right now? Can you guess? I mentioned you the names kinetic energy and potential energy. Since the bicycle is moving, we are talking about kinetic energy. Here in case of dynamo, the kinetic energy is being converted into electrical energy, which gives power to the lamp. Okay, so I hope you have now gained some concept about electromagnetic induction, its application in dynamo as well, which will help us in solving this question. Okay, this is a statement and argument type question. The statement says a bicycle dynamo can be used to power bicycle lights. Okay, let's see whether these two arguments support our statement or not. Argument 1, a bicycle dynamo generates electricity as long as the bicycle wheel is rotating, which is then used to power the lights. Argument 2, a bicycle dynamo requires a battery to store the electricity for later use when the bicycle is not moving. Let's look at our options. Option A, you can see only argument 1 supports this statement. What does argument 1 say again? A bicycle dynamo generates electricity as long as the bicycle wheel is rotating, which is then used to power the lights. This seems to be true, right? Because we just said that when we start to ride bicycle, it converts the kinetic energy into electrical energy. So as long as one person is riding the bicycle, the kinetic energy is there. So the generation of the electricity is also being generated. Now let's see about Okay, so argument 1 supports this statement. Okay, let's see whether it's only or both. Now let's look at argument 2. A bicycle dynamo requires a battery to store the electricity for later use when the bicycle is not moving. Okay, now let me recall to you about what I said earlier. I said you to imagine about generating electricity without using any source of voltage, right? So here, since we are talking about battery, means this statement seems to be contradicting, right? The bicycle dynamo does not require a battery. If it required battery, we would not be using electromagnetic induction concept in this case. So argument 2 does not support the statement. So with this information, I think you know the correct answer. Can you guess it now? Yes, only argument 1 supports this statement. Okay, so now another question. What effect does increasing the speed of rotation of the coil in a dynamo have? Okay, to answer this question, do you remember the example about, do you remember the second law of Faraday's? Yes, Faraday's law of electromagnetic induction. In second, we said that the strength of the magnetic field was what again? It is directly proportional to the rate of change of magnetic flux, right? So, let's see what does it has its effect. What effect does increasing the speed of rotation? You are increasing the speed of rotation of the coil, meaning you are also increasing the rate of change in magnetic flux. So option A says it decreases the magnitude of induced current. Is it correct? No, it does not decrease the magnitude of induced current. Option B, it increases the magnitude of induced current. Third, it has no effect on the current. And the last, it makes the dynamo stop working. I think you know the correct answer. It is option B. It increases the magnitude of induced current, because magnetic flux, because the rate of change of magnetic flux is directly proportional to the magnitude as well. Okay, students, I think now you have some basic concept about electromagnetic induction as well as its application in dynamo. We will continue our class in next session. Study well. See you soon.